The current-carrying conductor that attracted the iron filings is a very simple electromagnet. Let's examine the electromagnetic field more closely.
Here, a heavy copper wire has been inserted through a sheet of cardboard and connected to a DC source. Let's use a compass to determine the direction of the magnetic field caused by the flow of electricity. A compass is a device for determining direction by means of a magnetic needle that turns freely on a pivot. The colored part of the needle will always seek the Earth's magnetic north. Place the compass in proximity to the wire inserted through the cardboard and note the direction that the needle is pointing. Continue moving the compass to various positions around the wire, noting the direction of the compass needle at each point. The record of compass readings will indicate the direction of the magnetic field. Notice that in this graphic, the current is flowing downward through the wire from negative to positive. If the polarities are reversed, the direction of the magnetic field caused by the current flow will be reversed.
The direction of this circular magnetic field around the conductor is important for the operation of generators and motors. Here's a simple way to determine its direction. This length of insulated wire will be used to demonstrate. Curl the fingers of your left hand as if you're grasping the insulated conductor. Make sure that your thumb is pointing in the direction of the electron current flow. In this position, your fingers will automatically be pointing in the direction of the magnetic lines of force around the conductor. This is called the left-hand rule for conductors. Do not attempt to do this experiment without the supervision of your instructor. Electrical current can be potentially dangerous. The magnetic field produced by a small amount of current passing through a straight wire is weak and of little value.
The magnetic field produced by a current-carrying conductor can be reinforced or made even stronger if the wire is first wound into a coil. You can see how the magnetic field is strengthened in a coil by looking at this graphic representation of parallel conductors. Notice that lines of force pass around the conductors in the same direction. Because of this, the fields of each conductor add together to form one large field that envelops all of the conductors. Just as with a single conductor, when the polarities are reversed, the direction of the magnetic field is reversed as well. When a number of loops are wound in the same direction to form a coil, the magnetic fields of each loop interact to make the flux lines through the center of the coil more dense. The magnetic field through the coil becomes stronger. This produces magnetic poles with north on the end where the flux lines come out and south on the end where they go in.
The strength of the resulting magnetic field depends upon two things: the number of turns of wire, designated N, and the amount of current I.
For example, the strength of an electromagnet can be doubled by increasing the turns of wire from 40 to 80 or by doubling the current from 2 amps to 4.
In order to compare the magnetic strength of different coils, the magnetizing force must be determined.
This force, caused by the current flowing through the coil, is called the magnetomotive force, abbreviated lowercase m, lowercase f. The unit of measure for magnetomotive force is ampere turns, abbreviated with a capital AT. The magnetomotive force can be found using this formula: mmf equals I, the current in amperes, times N, the number of turns. For example, a coil with a current of 5 amperes and with 20 turns has a magnetomotive force of 100 ampere turns. Another coil with a current of 2 amperes and with 50 turns also has a magnetomotive force of 100 ampere turns. The magnitude of the magnetomotive force determines the number of flux lines there will be in the magnetic field. As the magnetomotive force is increased, the number of flux lines also increases. The strength of a magnetic field around a coil depends not just upon the amount of current or upon the number of turns, but upon both.
The magnetic field produced by a coiled current-carrying wire can be further increased by first inserting a piece of ferromagnetic core through the center of the coil. Remember, ferromagnetic materials have a higher permeability than air, which means that these materials permit the passage of many more magnetic lines of force than the surrounding air will. The material inserted into the coil is called the core. It concentrates the coil's magnetic field. Soft iron is used as a core in an electromagnet such as this one because it will retain only a small amount of its magnetism when the electric circuit is opened. This is called a temporary magnet.
You cannot control the output of electric generators and motors if you can't control the magnetism.
Temporary magnets are important. The electromagnet carried by this crane must be magnetized to pick up the metal and then demagnetized to let it go.
There are some devices that depend on principles of electromagnetism.
A solenoid is a device that enables an electric current to control a mechanical operation. A solenoid can be thought of as an electromagnet that has a movable iron core. Another important device is a relay. A relay is an electromagnetic switch. Unlike a mechanical switch, a relay can be located anywhere and operated remotely. As current flows through the relay coil, the magnetic field of the coil pulls down the armature, causing the contacts to close.
Let's look at one more device that depends on the principles of electromagnetism: permanent magnet speakers, which are commonly used in radios, stereos, and TVs.
A permanent magnet speaker is made from a paper cone and a permanent magnet. As you can see on this cutaway speaker, the flexible paper cone is attached to a cylinder with a coil of wire around it. One of the poles of the permanent magnet is positioned within the cylindrical coil. When current flows through the coil, it creates a magnetic field that interacts with the magnetic field of the permanent magnet, causing the cone to move in and out.
Stop the program and complete activity number 4. When finished, continue watching the program.